Hello students, now welcome back in physics class, and I'm here with a new topic, and this is the part 2 of the chapter gravitation. So today we are going to study a new topic of chapter gravitation. It is very interesting topic, and whatever I am going to tell you, you can practically do it. Okay? One thing, just I am telling to you, if you will throw a ball upside, what will happen? It will go at the some height towards upward, and after that it will again falling down towards downward. It is happening or not? Yes. Everyone, you can check it. You need to throw a ball towards upward. After some time it will start falling towards downward. Okay, so first of all, Galileo, have you heard the name of Galileo? Galileo studied about this motion, and where he did the practical at the Pisa, because his house was near the Pisa. So he went at the Pisa's top and start dropping the balls, start leaving the balls, and study many points about the motion of ball. Okay. After that, Newton came and he also increased that experiment. Whatever experiment done by Galileo, it means whatever the conclusion given by Galileo on that motion, by using those experiments, by those conclusion, Newton increased this pattern. Okay, in Newton take this experiment in forward direction. Okay class, and in some stories also it was saying that because when Galileo died, after 1 year Newton was born. When Galileo was died, after 1 year Newton was born. So some stories it was also saying that the soul of Galileo was inside the Newton, but what was the reality, we don't know. Okay, so just come back on our topic. So beta, when you need to drop a ball, so you can see it is downwards, always the direction of the ball towards downward or not? Yes, always the direction of the ball towards downward. And Galileo concludes that it is a kind of accelerated motion. This kind of, it is a kind of accelerated motion. Galileo told this, and what he told? He told one more point: the direction of this acceleration towards downward. The direction of this acceleration is towards downward. This is told by Galileo. Okay, and he also explained that the value of this acceleration is 9.8 meter per second square on Earth. He concludes 3 points. Who? Galileo. Galileo concludes 3 points. First is that it is a kind of accelerated motion. It is a kind of accelerated motion, and the direction of this acceleration is towards downward. Okay, and the value of this acceleration is 9.8 meter per second square. Okay class, after that what happened? After that Newton came and he also gave his theory, and this motion is this accelerated motion. This accelerated motion is known as free fall. This accelerated motion is known as free fall. And what will happen when you will throw a ball towards upward? So what will happen? Speed will decrease or increase? Students, tell me, speed will decrease or increase? Speed will decrease, because you can see it is moving upward, but after some time it will start falling towards downward. It means the speed of the ball is continuously decreasing. And you know, just Galileo told when the motion is accelerated, there is any kind of acceleration, yes, but the direction of the acceleration is towards downward. The direction of the acceleration is towards downward. Now, ball is moving upward, velocity is upward, acceleration is downward. Acceleration is downward, both are in opposite direction. Both are in opposite direction. That's why there the speed of the ball will continuously decreases. Got it? When it will start falling towards downward, in that case velocity is downward, okay, acceleration is downward, both are in same direction. If both the things are in same direction, so the speed of the and this motion is known as free fall. This motion of the object is known as free fall. Okay guys, and during free fall an acceleration is work, and acceleration is works that is known as gravitational acceleration. It is known as gravitational acceleration, and its value is already told by Galileo, that is 9.8 meter per second square. Okay, and one thing more, it is also known as acceleration due to gravity. Either you can say gravitational acceleration, or you can say it is acceleration due to gravity, and it is denoted by small g. It is denoted by small g. Clear class? Okay. Now more point. Now here you study small g. In video 2, in part 2, you have studied small g, and in part 1 of this chapter I have taught you capital G, universal gravitational constant. I have taught you. So in this chapter, one is small g, one is capital. What is small g? Just now you have studied acceleration due to gravity, and its value is 9.8 meter per second square. What is capital G? Universal gravitational constant, and its value is 6.67 into 10 to power minus 11 Newton meter square per kilogram square. Okay class? Okay, now more fact. One point. Now we are going to find out relation between small g and capital G. What the relation? How they are correlate? How we can correlate to each other? So see guys, now we are going to find out the relation between small g and capital G. Okay guys, so topic is relation between small g and capital G. Topic is relation between small g and capital G. What is small g? Small g is here acceleration due to gravity. And what is capital G? Capital G is here universal gravitational constant. Okay class? Okay. So see here, better let the mass of the earth is m. Let the mass of the earth be m. What I have told? Let the mass of the earth be m, and its radius is r. Its radius is r, but simply we are taking let the mass of the earth be me. Why me? Me stand for earth. Mass of earth and radius be r. R stand for radius of earth. Okay, and one object of mass m, one object of mass small m, one object of mass small m placed at the some height from the Earth's surface is placed at the some height from the Earth's surface, and the mass of the object is small m. So if any object, suppose it is the Earth's surface, suppose it is the Earth's surface and this is the center, and object is here, this is the object, and the mass of the object is small m. Mass of the object is small m. So this object is very small distance from the Earth's surface. From the Earth's surface, this object having this very small distance, and this is very small in the respect of radius of Earth, because radius of Earth 6,400 kilometer. So it is very small. So we can take it as negligible. Okay guys. So we will take this distance negligible. Now two objects are there, and in part 1 I have told where are the two objects doesn't matter. They will have a attraction force. They will have a attraction force between them. This force is known as gravitational force. So between the Earth and this point mass, between the Earth and this object, there is a kind of attraction force. This attraction force is known as gravitational force. So via the calculation, via the universal law of gravitation, we can write F is equal to G MEM upon RE square. This we can write, class. F is equal to G MEM upon RE square. Got it? Okay. Now another thing. This object is placed on the little bit height of the surface. So Earth will also attract this object towards the center. Earth will also attract this object towards its center by the second law of Newton. So what is second law of Newton? F is equal to ma. But here is the acceleration. Here is the acceleration due to gravity. That is F is equal to mg. Equation number 2. Now from equation 1 and 2. From equation 1 and 2. So students, we have two equations. F is equal to G MEM upon RE square, and second one F is equal to mc. Got it? So by the first and second equation, we can equate both, because equal things are equal to each other according to axiom 1. So we can write here G MEM upon RE square and is equal to mg. Now this m and this m is cancelled. So what is coming? G is equal to Gme upon RE square. So this is the relation between small g and capital Z. This is the relation between small g and capital G. Now see, small g is depend on this factors. So small g is depend on capital G. Small g is depend on capital G, and capital G to universal gravitational constant. Capital G is universal gravitational constant, so its value will not change. Okay. Now me stands for mass of Earth. It will also constant. There is no change of a small mass of Earth. Me, it is also constant. It is also constant. So that's why small g will also remain constant on the surface of Earth. On the surface of Earth, because this is free from the mass of the object. Small g is totally free from the mass of the object. It is depend on capital G, that is universal gravitational constant. It depend on the mass of Earth, that is also constant, and it depend on the radius of Earth. It is also constant. Thus, three are all the constant for the surface of Earth. For the surface of the Earth. That's why small g will also remain constant on the surface of Earth. And what is the value of a small g? It is small g is equal to 9.8 meter per second square. Got it, class? I hope you have understood all these things, and you need to revise these one, note it down. If any kind of problem you are facing, so please talk to me. I will remove your doubts. And in next video, I will tell you, is G everywhere constant? This thing I am going to tell you. Is G is constant in whole universe? If yes, so why? If not, then why? You need to also solve this thing, and I will explain this topic in next video. So please, you need to revise this concept. It is very, very important for you. Okay guys? Students, watch this video. It is an activity and it will very, very helpful to you. And after watching, you need to write down your observation and show to me.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.